Welcome to this part of the lecture on the circular waveguide. So, here we are going to utilize our previous treatment of the cylindrical wave functions, particularly the T to Z and the Tm to Z decompositions of the cylindrical solution to the cylindrical Helmholtz equation to the treatment of the circular waveguide, and see that they yield the propagation constant of the circular waveguide in terms of the T to Z and Tm to Z modes. We are going to compute the propagation constants, and also we are going to find out from these expressions the cutoff frequencies for the T to Z and Tm to Z modes and the characteristic impedances of the T to Z and Tm to Z modes. The circular waveguide. So, for the modes which are Tm to Z, we may express the field as we said in terms of the decomposition A equal to uz psi, or in terms of the substitution A equal to uz psi. The solutions we obtained for the electric and magnetic fields for this corresponding to this substitution A is equal to uz psi. Now, the field is finite at rho equal to 0. So, the wave functions must be of the form of 16. So, we wrote down in 16 that the circular waveguide, this is my circular waveguide. So, this is my circular waveguide, this is the center, this is my rho, this is my phi. So, because the point of interest includes this region which is rho equal to 0, the field decomposition inside the circular waveguide must be of the form of 16, where we use the nth order Bessel function of the first kind, okay, for describing the fields along the rho direction. So, therefore, we can write the psi function in terms of Jn k rho instead of e to the power j n phi, we can write that as sin n phi cos n phi, and for the forward propagating wave along the plus z direction, the variation of the fields or the appropriate eigenfunction is given in the form of e to the power minus j k z z. We call this equation 25. So, either sin n phi or cos n phi may be chosen. So, we have a mode degeneracy, that means two kinds of field distribution corresponding to the single eigen number n. The two distributions are equally possible, they are given by Helmholtz equation, they are equally possible solutions corresponding to a particular value of n. This is called mode degeneracy, except for the case n equal to 0, when sin n phi vanishes and cos n phi becomes 1. So, that means cos n phi becomes 1 means the field is phi invariant, that is it does not depend on phi. So, except for the case n equal to 0, we have the mode degeneracy along the phi direction. Now, if we go to the electric field expressions for the TM to Z mode from equation 21. So, from 21 we can write Ez as 1 by j omega epsilon, we deduce this del square del z square plus k square psi. That is 1 by j omega epsilon k square minus kz square psi, performing this differentiation corresponding to e to the power minus j k z z. So, we call this equation 26. Now, as per the conditions of the circular waveguide, because this is a PEC boundary, this is a conducting wall. So, Ez must vanish at rho equal to a, which is corresponding to the radius of the circular waveguide. So, we call this as a, which is the radius of the circular waveguide. So, Ez must be equal to 0 at rho is equal to a, and if Ez must be 0 at rho equal to a, that means Jn k rho a must be equal to 0, because that is the only way Ez equal to 0 at rho equal to a. From equation number 25 we substitute rho equal to a here, and Jn k rho a must be equal to 0 at rho equal to a. I mean, that is why we substituted rho is equal to a. So, corresponding to this, the eigenvalues for k rho will be determined. So, k rho will be equal to x n p by a, or k rho a is equal to x n p. So, these are the roots to this equation 27. So, x and p are the roots to equation number 27, corresponding to the zeros of the nth order Bessel functions of the first kind. So, we call this equation number 28. So, substituting this into 25, we get the Tm np mode function. So, which is psi np Tm will be Jn, instead of k rho we will substitute x n p by a. So, x n p rho by a sin n phi cos n phi e to the power minus j k z z. So, which is equation number 29, where n can be 0, 1, 2 etc., and p can be 1, 2, 3 etc. For a particular value of n 0, p can vary between 1, 2, 3, 4, 5, 6, infinite, it can take on infinite number of values. Then corresponding to n equal to 1, again p can take infinite number of values. So, as we said, so these are the roots to equation 27 corresponding to the zeros of the nth order Bessel function of the first kind. So, the electromagnetic field is then determined from equation number 19 and 21 with this psi function. So, we saw that 19 and 21 gives the electric and the magnetic fields of the TM to Z modes. So, the electric and magnetic fields for the TM to Z modes inside the circular waveguide can be determined from this psi function by substituting this psi function into equation number 19 and 21. Then the mode phase constant kz can be determined, because k rho square plus kz square is equal to k square, and we substitute instead of k rho x n p by a from equation number 28. So, because k rho square plus kz square equal to k square, this will imply x n p by a whole square plus kz square, that is equal to k square. So, this is equation 30. So, from this the values, the propagation constant kz can be determined at a given frequency for a given radius of the circular waveguide A for a particular mode corresponding to n and p. Similarly, for the modes t to z, they are expressed in terms of the electric vector potential f having only a z component of psi. So, this wave function must be of the form of 25. Okay. So, the wave function must be of the same form as 25, but we have to now substitute into the circular waveguide boundary condition corresponding to the fields of the T to Z modes. So, because E z is 0, we have to work with E phi, which will also vanish over the wall rho is equal to A. So, if so, E phi, which is del psi del rho from 22, must be equal to 0 or must vanish at rho equal to A. Rho equal to A. So, you can easily see that 22 gives the electric fields for the T to Z mode and E phi is del psi del rho. And therefore, if this has to be true, we differentiate once with respect to rho. So, therefore, J n dashed k rho A must be equal to 0 at, and therefore, J n dashed k rho A must be equal to 0. Now, we know that J n are oscillatory functions. We have found out, or we have discussed before that J n are analogous to cos k rho. J n k rho is analogous to cos k rho. So, they are oscillatory functions. So, J n prime or J n dashed k rho A must be also an oscillatory function. So, we can satisfy this equation, which is equation 31, by choosing k rho as x n p dashed by A, which is equation 32. So, x n p dashed corresponds to the roots of equation number 31 and also corresponding to the ordered zeros of the derivative of the Bessel function. So, from 32, the wave function for the T n p mode can be written as psi np Te as Jn. Now, instead of k rho we write x n p prime by A times rho the degenerate harmonic functions along the phi directions, which is cos n phi and sin n phi e to the power minus j k z z, where n is 0, 1, 2 and p is 1, 2, 3. And now, the mode propagation constant is again given by the same expression, which is k rho square plus k z square is k square. So, substituting for k rho we get, that is x n p prime by A whole square plus k z square is k square, which is equation number 34. Now, the cutoff wave number for a mode similar to the rectangular waveguide is that for which the kz will vanish, the mode propagation constant will vanish. So, from equation 30 corresponding to the Tm to Z mode, and from equation 34 corresponding to the Te to Z mode, we obtain Kc Np Tm as x n p by A and Kc Np Te we can write as x n p prime by A. So, k becomes equal to x n p by A for the Tm mode and k becomes equal to x n p prime by A for the Te mode corresponding to kz equal to 0. So, Kc becomes the cutoff wave number. So, if k is greater than Kc, we have a propagating mode, and if k so, if k is greater than Kc, we have a propagating mode, and if k is less than Kc, the mode is cut off. If we write Kc as twice pi Fc root of epsilon mu, we obtain the cutoff frequencies Fc Np Tm for the Tm mode as x Np by 2 pi A root of epsilon mu, and Fc Np Te the cutoff frequency for the Te mode as x Np prime by twice pi A root of epsilon mu. So, this is the cutoff frequency for the Tm mode, this is the cutoff frequency for the Te mode. So, we call these sets of equations 36. Setting Kc is equal to 2 pi lambda c where lambda c is the cutoff wavelength. We can obtain similarly and easily the cutoff wavelengths corresponding to the TM and TE modes as lambda c NP TM is twice pi a by x NP and lambda c NP TE as twice pi a by x NP prime. So, we call these equations 37. So, we see that the cutoff frequencies are proportional to x and p for the TM modes and they are proportional to x and p dashed or x and p prime for the TE modes from equation number 36. Now, the modes in ascending order of cutoff frequencies are TE11, the lowest order mode or the dominant mode in the circular waveguide, followed by the TM01, then TE21, then TM11 and TE01, which is degenerate with the TM11 mode. Okay, that means they have the same cutoff frequencies. So, the modes of the circular waveguide have the z directed wave impedances as we found in the rectangular waveguide, and we can find them out easily. So, for the TM mode we have E rho as 1 by j omega epsilon del square psi del rho del z, and this we can find substituting the appropriate psi function for the TM mode, and we can also find out h phi as minus del psi del rho, substituting for the appropriate psi, and then Z0 Tm is going to be given by E rho by h phi. So, if you do this, this becomes 1 by j omega epsilon del del rho of j n x and p rho by a sin n phi cos n phi minus j k z e to the power minus j k z z. So, one differentiation with respect to rho, another differentiation with respect to z, and this becomes equal to minus del del rho of j n x n p rho by a sin n phi cos n phi e to the power minus j k z or e to the power minus j k z z, and therefore, z 0 T m becomes minus j k z by minus j omega epsilon that is k z by omega epsilon. We call this equation number 38. And for the TE mode, if you have to compute E rho by H phi, we just find out E rho as minus 1 by rho J n x n p prime rho by A del phi of sin n phi cos n phi e to the power minus j k z z. So, that is equal to actually minus 1 by rho del psi del phi obtained previously. So, this expression has been obtained previously for the T to Z mode. Sorry, this should be minus 1 by rho del psi del phi, and H phi is 1 by j omega mu rho del square psi del phi del z, and that is equal to 1 by j omega mu rho j n x n p prime rho by A del phi of sin n phi, make it this cos n phi minus j k z e to the power minus j k z z. And therefore, from here we can find the z 0 T e as E rho by H phi, that is minus j omega mu rho by minus rho j k z. That is omega mu by k z. So, this is equation 39. So, this completes our treatment of the circular waveguide in terms of the propagation constant of the T to Z and the Tm to Z modes, the cutoff frequencies and the characteristic impedances of the T to Z and Tm to Z modes. Next, we are going to utilize the knowledge earned for the from the circular waveguide to the investigation of the circular cavity. Thank you.